Welcome to another edition of Common Algebra. This video is for Algebra 1, Chapter 3, Section 3, Similar Figures and Scale Models. So let's start with a few terms. First, the word model. A copy of an object made on a smaller scale than the original object. I think you're all familiar with perhaps a model train or a model car. They're just like the original, only they're scaled smaller. Which leads us to our next term of scale. The scale is the ratio representing the size of the model or the map compared to the object it represents in real life. Oh, for instance, if you made a model of a car, perhaps 1 foot of a car would equal 1 centimeter on the model. On a map, sometimes you see on the bottom of a map that 1 inch equals 100 miles. So the scale you need to know so that we can go back and forth, and from a small model or map we can tell how far or how big it is in real life. A scale drawing is when you draw a picture of an object with all the dimensions in the same scale to the actual dimensions of the object. A common example of this is the blueprint of a house. Next term is the term similar. Now we need to talk about this a little bit. Similar figures have the same shape, but they're different sizes. Oh, an example of something that would always be similar are circles. You could have a very small circle and a very large circle, and they're exactly the same shape, but they can be different sizes. Squares are another example that would always be similar. However, if you start talking about triangles or rectangles, then they're not always similar, and we would have to know, we would have to be told that they are in order to work with them. In these similar shapes, similar polygons, polygons just means it could be any-sided. You know, you could have 5, 6, 7, 8-sided figures. And whenever two different polygons are similar to each other, their corresponding angles are equal. The geometry word we use for equal is congruent. And corresponding sides of these polygons are in proportion to one another. And we're going to use those proportions to find missing sides. When we're naming similar shapes and sides that are corresponding to each other, the order is important and it does matter. So if we're told that triangle ABC is similar to XYZ, notice how I drew ABC in the same shape as XYZ, and since the letter A is mentioned first over here in the triangle, and X is mentioned first in its triangle, angle A and angle X are the same degrees. So that's what this is saying right here. Angle A is congruent to angle X, meaning their degrees are equal. B is congruent to Y, and C is congruent to Z. These are called corresponding angles because they're in the same location in their respective triangles. And now when we name these corresponding sides in proportion to one another, if I say AB, going from this angle, AB, then I need to say that that is in proportion over XY. You would not say AB over YX because angle A corresponds with angle X and B corresponds with Y. Likewise, when we talk about side BC, we say that that is proportionate to YZ. Since I said the B first, I have to say its angle that matches it, the Y. And then CA, we chose to say CA is proportionate to ZX. Now if I would have changed that and said side AC, that's proportionate to side XZ, and so on. We could make a whole bunch more of these equivalences, but just so you realize that the order matters when you are stating the corresponding sides in proportion. Now we're going to use the fact that the corresponding sides are in proportion to one another so that we can find side xy given that these two triangles are similar. So I'll just call side xy, I don't know, whatever letter you want. Why don't we call it Q? So we're going to find side Q here. Now what's difficult for me as a teacher is that there are so many correct ways to set up this proportion, I don't even think I could list them all. And it depends how you see it. Some people like to say that this side, CA, is to AB, and so they would say 5 is to 5.7 as 2.5 is to Q. And this would be correct, and we could solve for Q. Now, another person sitting next to you in class might see this differently. They might want to start with the small triangle, for instance, and say this side, XZ 2.5, 2.5 matches to side AC. So I'm going to put 2.5 over 5, and then that equals this side Q over 5.7. And you may look at each other's papers and say, whoa, that's wrong. But really, both of these are correct. And there's a lot more correct ways to set them up. You just need to be consistent. So no matter how you set that up of these two ways, we know that their cross products are equal. So we go ahead and multiply. Cross multiply, I should say. 5 times Q is 5Q. And now we have to multiply 2.5 times 5.7. If I did that correctly, I got 14.25. And then we divide both sides by 5, and we get Q is equal to 2.85. Now we need to discuss some different types of ratios, and we have to watch the units. The example we just did was working with the sides of the triangles, and sides are measured in linear units. Perimeter, if we were talking about the perimeter of any shape, that is also in linear units. But now we're going to ask to work with area ratios and volume ratios. And this is very, very different now. When we're asked to set up ratios with the areas of different shapes, we have to remember the area is in square units, and you can't use a linear ratio if you're talking about areas in square units. When we're asked to work with the volumes of different shapes, you need to remember that volume is measured in cubic units, and so you can't use a linear ratio for volume. You can't use an area ratio for volume. You have to use a volume ratio for volumes. So we need to know how to take a linear ratio and turn it into an area ratio. And that's what these two things tell us. This is very important to write down in your notes. If you have a linear ratio, for instance, if we have maybe one is 3 times another. We have a small shape to a large shape. So if we put small over large, 1 over 3. If this is the sides, the ratio of the sides of any shape, 1 to 3, we could find the missing sides or work with perimeter with this linear measurement. Okay, I'm back. I had to take a phone call, so now I got to pick up my train of thought. I think I was talking about the ratio of the sides of the shapes. And if we have the ratio of the sides, for an example of being 1 to 3, and then we were asked to do something with the area ratio, you can't use 1 to 3. You have to do what this says here. It says to square the linear ratio. So to get an area ratio with my little example here of 1/3, we'd have to square that. And then the area ratio, 1 times 1 is 1, 3 times 3 is 9. That's 1/9. And then if we had this same ratio of the sides and we were asked to do a volume problem, to get a volume ratio, we'd take that same 1/3 and we would cube it. Okay, 1 cubed is 1, and 3 cubed is 27. So that's just a quick example to show you cannot use the ratio of the sides in an area or volume problem. You have to square it for an area problem and cube it for a volume problem. So let's look at some examples of both of these. All right, in this next example of similar triangles, we are asked for a couple things. First, we're asked to find the missing sides, and then we'll go on to parts B and C stating the ratio of their sides. Now, sometimes they give you triangles like this, and we can tell that angle A corresponds to angle D, but one of them is upside down. Some of you are probably very good at seeing this even though it's twisted around. I am not, so I prefer to redraw the triangles facing the same way to make the problem easier for myself. So the first thing that I would do is redraw the little triangle with the angle A pointing down just the way the angle D is pointing down, and then this helps me see the corresponding sides better. So the first thing we're doing is asked to find the missing sides. So I'll call this one X, and we'll label this one Y, and those are the two sides we need to find. And once again, there's many different ways to set these up. You just need to be consistent. So if I'm going to find X, for instance, we need to have a proportion with 3 numbers in and 1 unknown. So this side 9 corresponds to the side 12 because AC corresponds to DF. So I could say 9 is to 12, and you'll notice I put the small triangle over the large. You need to be consistent. If you have small over large, then you have to have small, which is the 4, over the X, which is on the large. And then if we cross multiply, we end up with 9x equals 48, which gives us x is approximately equal to 5.3. Now we also need to find the y, and I'll set this one up differently, but again, you just need to be consistent. So if I start with the big triangle, 10 is to y, so I have big triangle over small. 10 is to y as 12 is to 9. And once again, we cross multiply. We would get 12y equals 90. And that gives us that y is equal to 7.5. All right, so we have found now the lengths of the missing sides. So let's look at part B here. It says, state the ratio of their sides. Well, it's probably easiest to state their ratio if you use whole numbers. So I'm just going to choose to put the small over the big. So I'm going to say 9 to 12. And if we're going to state this ratio, we do want to reduce. It reduces by 3. So it's 3 to 4. Now if you would have said 4 to 3, that's also correct, but just keep track where you have the small and where you have the large. In my ratio, I happen to put the small in the numerator and the large triangle in the denominator. And I'm just going to write that down for reference so I keep track of that. So this next part, this next question in part B says, state the ratio of their areas. The ratio of their areas is not 3 to 4. This is the ratio of their sides. So to find the area of their ratio, we take this side ratio and we square it. 3 squared is 9, 4 squared is 16. Now we have an area ratio that we can work with. So they have given us that the area of the small triangle is 27 square units. Find the area of the large. So just referring up here, I put small triangle over large. This is the area ratio. Small triangle over large, 9 is to 16. Triangle ABC has an area of 27 units, so I'll put that over x. And then we cross multiply to solve this. So 9x is equal to 16 times 27. which gives me 9x is 432. Dividing both sides by 9, I get x equals 48. So we have found then that the area of triangle DEF is equal to 48 units squared. All right, this next example is a volume question. We are given that these two rectangular prisms, like a box, are similar, and the corresponding edges have a ratio of 2 to 3. So I'm going to set that up as small over large, 2 to 3. We know that the volume of this larger one is 1,215 centimeters cubed, and they want us to find the volume of the smaller one. Again, we cannot use this ratio of 2 to 3. This is the ratio of the sides. We want to talk about a volume ratio. So we need to take this ratio and cube it. 2 cubed, 2 times 2 times 2 is 8. And 3 cubed, 3 times 3 times 3 is 27. Now this 8 over 27 is the ratio of their two volumes. So let's set this proportion up now. So I have small over large, and again, it doesn't matter which way you do it, just be consistent. We do not know the volume of the small rectangular prism, so I'll call that x, and we are given that the volume of the large one is 1,215. So now we need to solve this by cross multiplying. So I have 27 times x is equal to 8 times 1,215. When I multiply that, I get 9,720, and then divide both sides by 27 gives me that x is 360. So that means the volume of the small box is 360 centimeters cubed. All right, this is the last example. A toy manufacturer makes a scale model tractor with a 1 to 8 scale. So I'm going to write that as 1 over 8. The model is on the top. I'll just write that over here so we can refer to it. I put the small number, the model, on top, and real life measurement is in the denominator, 1 to 8. If a toy tractor has these dimensions in inches, what are the corresponding actual dimensions of the tractor? So this is like a three-part problem. So let's set up three different proportions. Now remember, we have the model or the toy is on the top, the real life is on the bottom. So the first toy dimension is 17.5, and we want to find the real life tractor dimension. So I set up the other two proportions here. 1 over 8 is 11.25 over y, and again 1 over 8 is 11.5 over z. So now I need to do some cross multiplying to find out the three measurements in real life on the tractor. So for x, I'm going to take 8 times 17.5 because x times 1 is just x. Also here to find y, we'll take 8 times 11.25, and to find the third measurement, we will take 8 times 11.5. So then when I multiply that out, I get that the first dimension is 140 inches on the real tractor, the second one is 90 inches, and the third one is 92 inches. So now I think you have the knowledge you need to do section 3.3, so have fun with math.